We were talking about the ionosphere being between the mesosphere and the, whoa, hope I didn't give you motion sickness there, between the mesosphere and the thermosphere. It's where you have solar radiation coming from sun. It's hitting nitrogen atoms and oxygen atoms here and stripping the electrons away, leaving these ions behind, these positively charged atoms without their electrons, the oxygen and nitrogen ions flowing around here. Now, this basically, because the solar radiation is hitting this, there's a certain reaction there, and at certain times of the year, when the solar winds, which give off strong radiation particles, these solar winds will cause it to hit this ionosphere, and it will create light, which is emitted to Earth, and this is what we call the auroras. Okay, the most common aurora. Now my brain's going to go dead. Borealis. There we go. Borealis, which means northern, called the northern lights. Borealis, toward the North Pole. And sometimes if you're in the northern United States, if you look up there, you can see these bright colors, and that's caused by the solar radiation hitting this ionosphere and causing this ionosphere, especially when there are solar flares, which are like big explosions on the surface of the sun, and it gives off more of these solar wind particles, radiation particles, that come shooting out and hitting the ionosphere here and creating the lights and so forth. All right. Now let's talk a little bit about what causes. Now, anytime someone from the scientific community wants to see how much the science the public understands, they want to make them really stupid, all they really have to do is ask them what causes the seasons, and a similar question, what causes eclipses. Now, we're not getting into eclipses right now. That's more the astronomy type, but the seasons really seems to blow people's mind. Okay, they don't really understand it. Now, we know we rotate around the sun. This is the sun. Now, this is looked at from an angle, so it looks closer here. But keep in mind, we do actually get closer and farther from the sun. It turns out that at this end, we're actually a little closer to the sun, and at this end, we're a little farther away. Now, this is not to scale, so this exaggerates how much closer we get. But just for the record, it can be a different distance of almost 100,000. I believe that's kilometers, which would only be 50,000 miles. But that's a fairly big difference, closer and farther. But and we know if you got close enough to the sun, then we'd be like Venus, where it burns up. Everything would burn up. If we go even to Mars, it's much too cold to support life as we know it. Okay, and so we do get a little closer and farther, but that is not what causes the seasons. In fact, we are closer to the sun during the winter time in the northern hemisphere than we are in the summertime. So it's not the closeness or farthest. How far we are from the sun. That does make small differences perhaps, but not enough to amount to anything. All right. Now, someone says, how can, it turns out that the main thing that does cause the seasons has to do with the angle of the sun, okay, hitting the Earth's surface. Okay. The Earth is tilted toward the sun when it's on this side. Sorry, if you're in the northern hemisphere, it's away from the sun in the wintertime, and it's closer down here at the bottom. And during the summertime, the northern hemisphere is tilted closer to the sun, and the southern is pointing away. Now we say it's tilted, but notice it stays that same tilt. As it comes around here, it hits it from the side, so it's kind of even, and it hits it from the side over here, so it's kind of even. But when it's the same tilt over here, now it's the opposite direction, and so you have opposite seasons. Okay. Now someone says, how can that make a difference? Well, here's the deal. If the Earth were not tilted, let's just say for a minute. Okay. Let's just say, oops, that kind of messed everything up here. Let me see. Okay. If the Earth was not tilted, it was right here, the sun would be hitting the equator straight on, and then it would be kind of hitting at an angle because the way the Earth curves here, it's like hitting it tilted. Okay, and so at the Earth's equator, where the sun's hitting directly, this amount of sunlight would be covering a spot like that. However, when it hits farther up or down on the Earth's surface, it would be kind of like we tilted the flashlight here, and now that it's hitting at an angle, that same amount of sunlight, no more, no less than was over here, is being spread out on an area that might be twice as big. Well, if you take the same amount of sunlight, and therefore sun's energy, spread it over twice as big an area, it's only going to get half as hot, or roughly you get the idea. It's going to greatly reduce how hot it is. And so normally it would be hottest at the equator, and then as you get away and you get more and more curved, you would expect the light to be spread farther and farther away. Okay, but when it's tilted over here, it doesn't hit at the equator. It's hitting directly right here about the Tropic of, I believe, Cancer is the one down here, and Capricorn is the one down here. It's about 15 degrees off. So that's it. And everywhere up here is getting getting closer to this kind of picture where they're getting a more concentrated dose of sunlight, if you will, and so it is warmer up here in the northern hemisphere. But the southern hemisphere is tilted away, so they're getting more of a tilt, okay, and they're getting more of this down here, and so they get a less concentrated sunlight, and therefore they are in their winter. Okay, now when we're here and here, we're not tilted toward or away from the sun, we're tilted kind of off to the side, and so the equator is in fact getting the most sunlight for the most part right there. Okay, and here and on the other side of the earth, of course, we'll be getting sunlight, but there you go. But when you get over here again, now it's tilted away, so we are tilted away, so we're getting more of an angle when the sunlight comes and hits us. So we're getting this angled type where it's less concentrated, and therefore we tend to have cooler temperatures. Okay, now in the southern hemisphere, they're actually getting more concentrated, so they're summer, if you will, would be in December, whereas their winter would be in June or July. So even though we got to name the seasons, people from Europe and other countries like that got credit for naming them, therefore they named it for their seasons, not the southern hemisphere's seasons. They experience very different seasons. But the tilt of the earth toward or away from the sun affects the concentration, if you will, of the sunlight. And that is what causes the seasons. It has nothing to do with how close or far we are from the sun or anything else like that. Okay, it's just the tilt of the earth and how that changes the concentration of sunlight. I'd like to talk about radiation and solar radiation versus terrestrial radiation. Okay, solar radiation is radiation coming from the sun, and when it comes toward the sun, toward the earth, it includes obviously light. It also includes heat or infrared radiation, which is going to be heat. Infrared lamps are used in fast food places and so forth to keep food warm, restaurants, things like that. Okay, light, you have above the light, you have the UV rays. A lot of that gets blocked, but not. Okay, now all this radiation hits the earth. Okay, notice it mostly passes through the Earth's atmosphere. Okay, here would be the atmosphere we've been talking about around it. Most of this just passes through the atmosphere. It's not absorbed by the air until it hits the Earth. Now, when it hits the Earth reflects some of the light back off, just like the moon reflects light back to us at night. We see the sun. What we see of the moon in the sky is some of the light being reflected, but it's not a great reflector of light. Most of this energy, this infrared light and UV, is radiated back off as infrared. IR, infrared just meaning heat. Okay, and so terrestrial radiation is the radiation coming off the Earth, going through the atmosphere and back out into space. Okay, now our sunlight lets most of this light come through. Okay, and the UV light. Okay, but when the infrared from the Earth comes off, infrared is absorbed by the atmosphere better. Okay, and so it actually warms up the atmosphere. We also have it warmed up because the surface here warms the air, and then the air rises, and we'll start talking about that here in a minute. Okay, but in general, what our temperature of the Earth depends on the amount of radiation coming in from the sun and the amount of minus the amount of infrared radiation that we send away from that. Okay, during the daytime, there's more coming in than we're giving off, so we have a net gain, and during the daytime, the temperature heats up. All right, but at night, since we're on the other side, on this other side of the Earth, we are still giving off infrared, but we're not getting any new sun radiation coming in, so at night there's going to be a net loss, and so the temperature goes down. If you have thick clouds keep some of this incoming down, so it doesn't warm up as much during the day. Okay, But on the other hand, it also keeps this infrared from leaving at night, so we don't have as big of a loss. And so basically, cloudy days keep it from being as hot in the daytime, and it tends to keep it from getting as cold at night. Okay, usually when you have hard freezes and stuff, it's usually when there's a clear sky. Now, there's also air masses of different temperature moving around that can affect that, but in general, the cloudier it is, it's not going to get as cold at night, but it's also not going to get as sunny during the daytime. Now, the Earth's atmosphere kind of acts like a greenhouse for us in that sunlight, visible light comes off, we let out this infrared. This infrared can be absorbed, especially by what we call the greenhouse gases. Usually we think of that in particular, the main gas being involved here is CO2. But there are some other ones, but CO2 is one of the biggest ones, and it absorbs this and it keeps us warm. Okay, it keeps the atmosphere, gives us nice, as it absorbs that radiation, infrared radiation, it keeps the atmosphere warm and traps heat, and that keeps us from getting really cold at night, which might happen if we did not have that atmosphere there. It gets so cold things would die. Okay, and so this is very important. Now, greenhouse gases always happen. It's what makes life on Earth possible. All right. Now, we, though, have changed that because we are burning massive amounts of coal and gas and gasoline and oil and various things, all these things that contain carbon and give off carbon dioxide, and we're giving off massive amounts of them. Okay, and so it has led to what we call global warming. Okay, greenhouse gases have always been here, and we've always had them. It's just that as we increase the carbon dioxide levels, okay, we have seen an increase in the temperature. And if you look back in history, what we've recorded history anyhow, 1850s or so is about when we first the Industrial Revolution and factories started using burning lots of coal, and you see a general trend over time of an increasing global temperature. As it increases, it goes. Now notice that at any given time, from year to year, it may go up and down, up and down, up and down. Way down in here, we had some really cold times. Boom, there's a real cold one, but it came back up, then it got real hot, and then it went down, went back up and down and down. But overall, especially in the last 20, 30, 40 years, you're seeing a much steeper climb here. Okay. Now, keep in mind, in the Earth's history, there have been times when it's gotten hotter, and there's times when it's gotten colder. There's times we think there were no ice caps at all. They were all melted down. There are times when we had ice ages where it covered a great deal more. And obviously, this is the carbon dioxide level rising. There were still days, actually years when it was colder, and then there's years here where it didn't rise that much, but it got hotter. So obviously, other things are affecting it other than just our production. But on the other hand, you can see that overall there is this definite, yes, it may be colder than it had been here, but that's a lot still warmer than it was in these years when it was really, really high. So overall, there is definite trend toward warming. Are we creating more carbon dioxide and therefore increasing the greenhouse gases and therefore increasing the temperature rise? Yes. Okay, that's not really up to debate. Now the question is, how will that affect our weather? How will that affect our planet? Will it cause us to become dry, or will it just become warmer and perhaps moister and then more like a junglish thing? Or will it cause more desertification where areas get hot and dry and you end up where you can't raise crops? Say if that were to move up in, say, the Midwest where we produce all our wheat and so forth and corn and gases like that, then that would have severe effects upon us. But exactly what will happen in the future, how this will change the climate. We know it will change the climate, but it's really harder to say exactly how will it and how much of this is natural, that we're just in a warming trend, or how much of it is man-made, how much of it is caused by man and therefore is man-made, and how much can we control that by controlling the amount of carbon emissions we give. That's what is not so for certain. Okay, that's where it gets iffy, and some people go drastic predictions of horrible things are going to happen to us. Others say, oh, the whole thing's just a hoax and it's alternate news, and that's both of those stands are probably kind of idiots. Okay, but it is something we need to be concerned about and aware of, and hopefully monitored. And anything we can do to reduce the effects of that. We're not going to just quit burning coal and gas and stuff for electricity and give up our cell phones and give up all our gadgets and computers and whatever until we have to. But on the other hand, it is a legitimate concern and something we should be concerned about. It's not just fake science or something like that. There is global warming happening. To what extent it will continue to warm up and what the effects of that will be, that we can't be so definite about. But it definitely is occurring. The last thing we're going to talk about with the atmosphere before we get into just weather proper and talking about weather is that as air heats up, it's going to rise. And where it gets hottest, at the equator, it's going to start to rise. Okay? And then we're going to look at how it happens and how it causes air to circulate and how we have winds and so forth. And because that's kind of one of the driving forces behind our weather. And we will do that in the next video.